mature and thing. Okay, so that of course we also mention about this kind of we do spend time introduce this kind of ITRS. ITRS means International Technology Roadmap for Semiconductor, and it's global. This kind of consensus. No, that means leading semiconductor company and leading the kind of semiconductor country and region. They make this kind of roadmap, so that I would mention this thing is so that all of you enjoy this kind of advanced semiconductor for your smartphone, your computer, and your smart watches, and then so that we are in the this kind of new stage of all the microsensor and actuator and biochip. So this is something quite important. I also mentioned that at this moment, I would say COVID-19, we actually were in the stage of IoT, right? In the internet things, so that everything we online, we go online teaching, online exam, and then so that of course, hopefully in the near future, we'll not only use webcam. In the future for online teaching, we may use this kind of VR, AR, MR. It would be more interactive, right? So you say webcam for online teaching, it's okay, but can we use 3D sensor, 3D so that the VR, AR for this kind of online teaching have more this kind of realistic, this kind of online teaching? What do you think? And actually, if you look at, for example, Facebook CEO, right, Mark, he changed the company to Meta, and also he introduced this kind of how this kind of Facebook or Meta, they want to develop this kind of VR, AR. So you see this kind of thing. If in the future we can use this kind of VR, AR with 3D sensor or virtual reality, this kind of headset, so that we can have more interactive way for this kind of online teaching. I do think it will be quite important, right? Of course, we all this kind of a sensor with a camera, how we can use AI, so that that will become also quite important. And another thing is not only sensor, we also have actuator. For example, a man's micro mirror, why it's actuator, so that you see actually a Microsoft HoloLens 2. I should emphasize that, for example, Microsoft man's micro mirror, why is actuator, micro mirror. So this is something quite important. It's not only for computer projector, and also for this kind of AR or MR. So that if you look at Microsoft, this kind of HoloLens 2, actually they use this kind of micro mirror, okay, for their this kind of AR system, okay, for this kind of AR, okay. So that this is something I told you, main sensor actuator become much more important, and biochip, of course, as I mentioned, so there's a important, especially COVID-19, so that it's important how we can make this kind of micro biochip or microfluidic device at lab on chip for rapid detection of COVID-19. Right? Or I do have an ongoing project, plasmonic PCR chip integrated with biosensor using this kind of TSMC semiconductor biosensor for rapid detection of this kind of COVID-19, this kind of RNA. So this is something I would say is quite important in SC. Okay, and okay, so I think we also let you to see this kind of a video about this kind, how this kind of micro machine work, and then also I will say quickly show you about data fabrication, right? So that again, we are in this kind of a spatial thing, not only smartphone, but smart watches and smart car, smart building. So that I just emphasize that especially this course related to the building, while we talk about smart building, intelligent building, so that how we have low cost microsensor for building application, right? You can use this kind of VAV, variable air volume, this kind of thing to do this kind of demand control ventilation, right? For air continuous system, and then you have additional this kind of micro sensor for indoor air quality. Look at some of this kind of CO2. Typically, one of the most mature is this kind of CO2 sensor. CO2 sensor is used in especially use NDIR, this kind of optical near infrared. They have a sensor to detect CO2 for this kind of demand control ventilation. That means if you are able to detect this kind of a concentration of CO2 inside the building, we are able to see how can you adjust this kind of air conditioning system, right? So that provide enough this kind of oxygen from outdoor fresh air. So this is quite important thing. Okay. Anyway, so of course we also show you that in the near future, I think it's possible we may also have additional this kind of motion sensor for structural health monitoring. Unfortunately, you can see in the past 1 or 2 weeks, we see the earthquake in Japan, earthquake in Taiwan. So that I think Hong Kong got very, very tiny earthquake. So that at least 1 or 2 days ago, at least my hometown Taiwan, actually we have more than 6 scale this kind of earthquake in east part of Taiwan, and Japan also have quite severe earthquake. So that can we use this kind of a man's motion sensor as barometer to monitor this kind of health condition of the building or even the bridge, so prevent this kind of disaster. You say once a big earthquake, and then unfortunately people will die. I still remember like almost 20 years ago, year 2000, Taiwan has earthquake in Taichung, and then it's about more than the scale is 7 degrees, 7 risk scale, so that almost 2,000 people die. Why it's really sad, but I just unfortunately Hong Kong we're lucky, but many other parts of the world actually suffer this kind of earthquake. And of course, I understand that in Sichuan we also have that big earthquake, right? So that this is thing, can we really use kind of low-cost main sensor to do the health monitoring of the building structure? I do think it's important, right? So that this is important to enhance the safety. Okay, so anyway, so that I just tell you this is the same. Oh, as I told you that I do have several years ago, I have a project how to come with the most main sensor. Right, look at the thermal flow sensor, temperature humidity sensor, and then look at thermal comfort, and then the kind of smart personalized ventilation, smart window, and then building expert work on this kind of CFD simulation and AI, so that we at least demonstrate we're able to do this kind of smart HVAC to reduce the kind of energy consumption for at least one room at UST, while we can save about 20% of energy. Okay, and then maintain good this kind of thermal comfort, right? And so anyway, so I just tell you this is something quite important and thing, so that I do think this kind of micro sensor will be really change the world. So that it's not for me, but it's all the big company. Apple hire a lot of this kind of man's engineer, right? So that so this is something I tell you is quite important. I think we may also want to go back to that. Let me see. We didn't finish that video, so that I do think would be important for you to watch that video. Of course, as I told you that this video has copyright, so I will stop this kind of streaming on YouTube to prevent this kind of copyright problem. But so anyway, I just tell you, I think it's useful for you to watch, continue watch this kind of video, and then so that let me quickly go back to this lecture. Yeah. So again, this video is one of, I think, best video, so that it's unlisted, so that because it's a copyright issue, so that at least I just let me quickly just look at this. Again, all the kind of microfabrication process involve 3 steps: etching, first patterning. You have design of micro machine or microelectronic transistor, and then from computer software like a Cadence or our for MEMS, we use another EDA tool like edit, and then once design and then do the patterning, and then patterning in see, this is a photoresist or this kind of patterning, right? And then photoresist, photolithography, and then we try to do etching, deposition, and doping. All this thing, no matter how complicated is this kind of micro machine, I think we have this kind of typical fabrication process based on this 4-step. Okay, patterning, right? That means you have a design of an optical mask design, and then you're using photolithography patterning, and then you do the etching, deposition, and doping. Okay, let me try to think. I just tell you this is something I do think is quite good for you to have a real understanding and try to. Although you cannot go into a clean room, UST do have very good clean room. So that at least here you can look at how it works.
The wafer moves to the ash chamber, where the photoresist and etch residues are evaporated to the I-line stepper. Here, a light source of a specific wavelength filters through a mask and a lens to expose the wafer. The resist is positive. The areas exposed to light are changed chemically. The wafers move back to the track system. Here, developer is puddled onto the wafer, and the exposed areas are rinsed away.
It's a photolithography.
To ensure quality, measuring feature size is important throughout the process. This SEM, or scanning electron microscope, is measuring the dimensions produced by the photoresist process. The exposed metal will now be etched using plasma. In this chamber, chlorine-based and inert gases etch the aluminum-copper alloy. This defines the resistor leads and removes the highly conductive aluminum-copper layer from the area where the resistor material will be. While still under vacuum, the wafer moves to the ash chamber, where the photoresist and etch residues are evaporated and pumped away. The resistor metal is now deposited. After the wafer surface is conditioned, it goes to the sputter chamber, where a thin layer of resistor metal is deposited. Photolithography once again patterns the resistor metal layer. In the plasma etch system, the resistor metal layer is etched from unwanted regions. When current is eventually forced from 2 metal layers to 1 thin metal layer, it will create the heat that fires the resistors. A thin film stack of 3 layers will now be deposited on the resistors to provide electrical, chemical, and mechanical protection. This system deposits the first 2 dielectric layers over the resistor. The first layer will provide electrical isolation between the ink and the firing resistor. In the same chamber, new gases deposit the second layer, which protects against the corrosive chemical attack from the ink. The third protective layer is metallic, so it can resist the mechanical forces of the collapsing bubble. The wafers go into a sputter etch chamber to prepare the surface, and then into a sputter deposition chamber, where a thin metal layer is deposited. Now that the resistors are protected, the chamber walls where the vapor bubble forms are built. The wafers are washed and prepped. A deionized water and ozone treatment removes any residual materials that might remain on the surface from previous steps. The deposition of barrier material used for the chamber walls is similar to the photolithography process. As the wafer spins, a thick negative resist-like material is spiraled onto the wafer. In soft bake, the solvent is slowly driven out to set the barrier material and make it more uniform. In this bake and expose system, the wafers go directly to the stepper where they are exposed. As a negative resist, the barrier material exposed to light forms a polymer and hardens. Because this resist is so thick, the exposure times are much longer than for standard photoresist. After exposure, the wafers move to the bake ovens. The areas exposed to light induce cross-linking and become a permanent part of the chamber. The non-exposed areas are removed when developed. Instead of the usual puddle develop, spray develop is used here. Spraying droplets of developer provides a higher surface area that can attack the thick barrier material more easily. A big open chamber now exists. We can see that small pillars have also been created from the barrier material. These pillars at the entrance to the chamber serve as a filter to block particles that might be in the ink from clogging the nozzle. After develop, the wafers are placed in an oven, exposed to higher temperatures, and allowed to cure. Thickness measurements are made after each layer is cured. A thick photoresist resin, called a sacrificial wax, is spiraled onto the wafer and spun. The wax fills the cavity and covers the entire wafer. A soft bake sets the wax, and a portion of it is removed to bring it flush with the chamber surface. The wax holds up the shape of the chamber as the building process continues. In a dry process, a layer of barrier material is pressed onto the wafers to create the nozzles. The nozzle material on this roll is sandwiched between two protective sheets of carrier films. The dry application will minimize the interaction between the nozzle layer and the sacrificial wax. Here, the bottom carrier film has been peeled away, and we see the nozzle material placed directly on the wafer. After the dry film is applied, a blade cuts around the remaining films, and a new layer is prepared for the next wafer. The robot moves the wafer with the nozzle material and its carrier film to the next stage. In a separate tool, the carrier film is removed. A strip of tape is rolled across the wafer, and a pickup roll lifts the carrier film off. Photolithography is now used to create the nozzle orifice. The exposed areas become cross-linked and remain a permanent part of the print head. When developed, the unexposed nozzle material and the sacrificial wax are removed. The wafers undergo a final cure. To create the channels the inks will flow through, a laser and etch process forms a trench between two rows of nozzles. Inside the laser system, the wafers are placed backside up. A pulsating laser scans the back of the wafer and defines the dimensions of the slot. Without breaking through the silicon, it then drills a deep, narrow trench within the slot. The final slot shape is created in a bulk etch process. In this anisotropic etch, chemicals such as KOH and TMAH etch the silicon crystal and remove the remaining thin silicon layer left after laser micromachining. Wafers are automatically mounted onto a ring and tape. This holds the die in place as the wafer is sawed into individual units. Following singulation, the wafers are rinsed and dried to remove any particulates. In a final visual inspection, only the functioning die are examined before they are shipped. The camera on the microscope is programmed to recognize certain patterns. It highlights defects for the operator, who then confirms or rejects them. The sawed wafers are packed and shipped to various HP sites. There, the good die will be attached to a pen body like this one which is becoming a permanent fixture in printers today.
Okay, so some students say actually this part has been watched.
Optical MEMS
so I think we
manipulate
may
light.
skip this part. So
The packaging process
maybe we
begins
try
with
to
the
go
removal
skip
of the
to
spacers and protective photoresist. The wafers with epoxy.
I think I do think you have
The
rushed
glued
down
wafer
this.
and window are then transferred to the bonding chamber, where ultraviolet light, heat, and pressure are applied in a vacuum.
So I don't know if you
Back in the
already
clean room, epoxy is dispensed inside.
So I see some students mentioned. I think we have some overlap, some video clip, so that maybe we can skip. Let me check. One student said you don't need to memorize the part, but at least this is a additional information, the video for you to understand those kind of lecture note. Do you understand? So because I do think you compare with those lecture note, this video can really let you see why all the key this kind of real how with this kind of a very short period of time you can really quickly understand how to make this kind of thing, right? How this device work, right? How we can make this thing. So this is I do think this it is give you some I do believe this kind of video is quite useful.
The mirrors flip back and forth continuously.
But do you understand? So another key important is to let you know this device can
The
only
screen
make
shows
by
the checkered
one
pattern
company.
of the pixels as they flip.
Remember, so
To
TI
overcome
spent 20
station,
years.
the tendency for surface.
Do you understand? Tesla Instruments spent 20 years to work on this DMD chip. So then the question is, you look at the video, can you understand? And then if you are really learn about this kind of thing, then you can become rich. Because just a thing, right? There's only one company can make this TI chip. So that I do know that many companies in Asia, Taiwan, China, and many places, even Japan, want to make this DMD chip, but no one. Oh, one still saying, what is the DMD function? DMD can be used for computer projectors, and also can also generate some this kind of new product. I will show you later on. I think the quite important student will ask. DMD, one of the major application is about the computer projectors or some this kind of a thing. So this the major application. One student asked about major application of DMD. DMD while micromirror is at least in mainland China, like across the border is computer projector, or some pico projector, portable projector. You can carry very small projector. So of course, micromirror can also use for the HoloLens too, VR AR function. Micromirror DMD is one. There's a series of things. Of course, micromirror can also be used for this kind of main LiDAR. Okay, that's quite important. I mentioned LiDAR also need micromirror. Okay, so it's a quite important technology. At least I have one peer student work on this micromirror using CMOS or TSMC technology. So it's at this moment only one company can make this one.
Small
TI.
structures to stick. The mirrors rely on the restoring force of the torsion hinge to
Basically
return
apply
to a
the
flat,
voltage.
on or off state.
Apply voltage, and then so it can generate electrostatic force.
Looking closely at the
Right?
yoke,
We
we
can
also
turn
find
left
small
and right.
spring tips. These tips deflect slightly as they land on the lower surface. When released, the stored potential energy provides a slight kick that helps overcome.
I mentioned, that's some interesting thing, you see. This is some contact. So that the micromirror touch on the substrate of this kind of a silicon wafer, and then sometimes there's some stitching problem. So that this actually is some much more complicated. It's non-trivial. That's why TI spent 20 years to make this work. From demonstration working in the lab to mass production, increase the yield. Wow, it's a spend $1 billion, 20 years. It's really non-trivial.
Adhesive forces. After burn-in, a tester measures whether or not the mirrors tilt. A second tester checks the mirror movement by applying various voltages and measuring the responses. These movements can vary between devices with different angles and mirror sizes. The final test is a visual test. The image is projected using different colored screens and inspected to ensure there are no defects. A defect projected on a black screen, for example, may not show on a dark background, but will show when projected against a white background. Here we see a test device which has been programmed with specific images. The mirrors reflect the image in black and white. These same images, reflected from the DLP device, go through a series of lenses and color filters to be projected in color. A laser brands the appropriate information on the back of the DLP devices before they are shipped to the suppliers around the world. They, in turn, produce the many projectors we use on a daily basis. To see how sensors are designed, let's go to Freescale Semiconductor. Designing MEMS devices is a critical part of manufacturing and a team effort. Experts bring together the mechanical and electrical design and manufacturing aspects to create complete microsystems in different fields. Two of the most common types of sensors monitor pressure and movement. Pressure sensors measure pressure change in gases and liquids. In most cases, a thin silicon membrane responds to a change in pressure and triggers a response. This requires an opening in the package to keep one side of the membrane exposed to the environment. In cars, they monitor things like combustion pressure to improve fuel efficiency and side crash detection. These sensors monitor the air pressure of tires. These monitor blood pressure. Inertial sensors measure a change in movement. They include accelerometers and gyroscopes. Accelerometers measure linear movement along the X, Y, and Z axes. They detect acceleration, which is a change in speed or direction. They are used in cars for safety-critical applications to improve dynamic control. In this electric car, they deploy airbags, while pressure sensors monitor tire pressure.
36 psi rear.
Accelerometers are found in a variety of motion detection consumer products. In sports, like golf, they provide information to help improve one's swing.
A lot of measurements. If we keep that shoulder tilt down.
Gyroscopes measure rotational movement, known as yaw, roll, and pitch. These gyros are used in cars. When they sense a car has lost control and begins to roll, they deploy a side airbag. The design of sensors and MEMS in general is done in an iterative top-down workflow that requires revisions and feedback. This process typically begins when the customer presents requirements to a team of mechanical, electrical, and systems engineers, as well as marketing and sales experts.
There are some things here that we have changed the way we're doing with the next line of cars that we're going to be looking at. You all were proposing a digital data output, and we think we'd like it to have an 11-bit.
To be able to still meet that same timing.
To still be able to meet that same timing.
Which is most important, Daryl, the package change or the 8-bit to 11-bit?
We did anticipate you might have some challenges with going from the 8 to 11-bit.
It's just that, going from an SOIC to a QFN, it just takes 3 months for a qualification.
I would assume that with your new requirement for 11-bit, you would be able to get into the next model year and still be fine.
At a later date, we could provide the additional 11-bit ADC conversion.
That might work.
The project requirements are then presented to the design team, who scope the project and establish a roadmap.
What we learned in the first meeting is that they not only want a digital part in SOIC 16, but they also want a digital part in a QFN and an analog QFN by the same schedule, by the same time.
So the package, I'm a little concerned about that.
8-bit to the 11-bit, and the filter options, they want a tighter accuracy.
I know Aaron's done some simulations before on the G-cell in that package. Do you have some thoughts?
Yeah. With this HARMEMS, or high aspect ratio transducer, we may have some challenges in that area.
And possibly if the package as well, so I would need to get a package model from Aaron.
So then I guess we'll try to arrange with the customer to get some extension for you guys, and then we'll just meet again here internally.
That would be great.
Let's take a look at the project from the different perspectives of the designers who are working on it. The mechanical designer determines the limitations of the mechanical transducers. This is the part that converts motion into a change in electrical signal, such as capacitance. This signal is read by the electrical or application-specific integrated circuit, known as ASIC. With accelerometers, an abrupt motion or acceleration moves the proof mass. Each sense electrode, connected to runners, collect the change in capacitance signal. The runners, connected to electrical leads, carry the signal to the ASIC. The ASIC designer checks that the change in capacitance, which is converted to a voltage, meets the circuit's requirements. The systems engineer creates an architectural level design and writes the specifications. These specifications can include the level of integration or layout of the device. With system in package, a sensing cell measures the force of acceleration, which results in changing capacitance. Freescale's IC design converts capacitance to voltage and allows the sensor to be calibrated or checked for accuracy. This particular sensor is used in the game Guitar Hero. Some sensors bond the die in a stack formation to reduce the footprint. Here we see the pressure sensor. On the other side, we see three devices: the microcontroller, radio frequency transmitter, and a dual-axis accelerometer. These stack devices can track the motion in golf swings. In cars, they monitor sensors without using wires.
It's picked up by basically a sensor or a receiver that's integrated within the wheel well of the vehicle itself.
After scoping, partitioning and model generation is the next phase. Here, the Microsystems Group partitions the components of the system into blocks that represent the physics of the mechanical and electrical chips. Each block has a mathematical representation that consists of lines of equations or code. The design often starts with a few lines of code. More lines are added to enhance the model's details and set the operational parameters. The transducer model allows designers to predict proof mass motion. They do this by applying different accelerations to the model. The calculations they use address issues like mass and stiffness of the proof mass and the change in capacitance. Other equations determine electrostatic attraction and internal gas resistance that dampens the motion. The package model determines the effect of the packaging, including stress, on the performance of the MEMS chip. The result is a transducer systems block that predicts the changes in capacitance. These changes will be monitored by the ASIC logic chip. The ASIC designer works on the conversion of capacitance to voltage. The voltage is then sampled and converted to a digital signal. The designer then applies final digital algorithms. Some of these will be used to set up the conditions for the final testing. Once the system engineer feels comfortable with the partitioning and modeling of the MEMS and ASIC designs, the work progresses to the analysis phase. Here, the systems designer brings the two together to find out how they work. MEMS and ASIC blocks simulate performance and ensure the results meet product specifications. While the design needs to be represented in a mathematical format, it also now needs to include the impact of fabrication. With surface micromachining, deposition, photolithography, and etch produce feature sizes that may not exactly match the design. The designers need to know how the process works. For example, a deep reactive ion etch, known as the Bosch process, creates deep straight-etched walls by alternating chemicals used in the etch chamber. These high aspect ratio structures increase the surface area of the sense elements vertically. As a result, the chips will need fewer elements and can therefore be made smaller. Designers make adjustments, and data moves up and down the process flow 2 to 5 times or more. Models run over and over again as areas are repartitioned or variations tightened. Before the process finishes, the final data is checked against the design specifications again. In verification, the systems engineer receives and checks analysis data. The mechanical designers verify their MEMS design with layout 2D CAD tools. And circuit designers execute and verify with transistor-level schematics. Once cleared, the mechanical and electrical designers create their final designs, known as tape-out. The project then moves to fabrication. There are many types of MEMS devices. Biochemical microarrays printed with stacks of specific peptide sequences and used in DNA studies can quickly identify the existence of cancer. Tiny cantilevers or probes used in the atomic force microscope map the surface of atomic structures. MEMS serve as a bridge between the micro world and the even smaller nano world. As technology moves forward, the potential of MEMS devices is vast and limited only by our own mechanical ingenuity.
Okay, so I don't know if you do we have any question about this video in terms of several devices, right? Including this kind of DMD, digital micromirror, microfluidic, and this thing, and this MEMS sensor. Do you have any question? Any question about this video? Huh? I do one student asked about what's the DMD or micromirror application, or it's a quite important technology. It's something can lead a $1 billion business. I'm not joking. So that this thing, of course, in the video, I don't know if you know that in the video there's one particular thing about. Let me show you that the video. There's one at the end of that video. I don't know if you see that the spatial this one. Let me show you this one. Let me show you this particular one. So this is called the OET, optical electrolyzer, invented by my UCF friend. Actually, he become Professor Everett Cho in Professor Ming Wu's lab. So that they published the paper. It's called OET, optical electrolyzer. Okay, so that means using light. Actually, use DMD, digital micromirror, so that we can, with AC electric field, we can apply some force. Okay, to manipulate the cell, biological cell, so that this is one important technology invented almost 15, 16 years ago. And you know what? And then this create a company. Can you believe? Huh? This company, Professor Ming Wu's company, actually he do an excellent job for this device, published paper in Nature 2005, and eventually his company, he continued to develop this kind of real product, and his company called Berkeley Light. Berkeley Light actually become IPO. Okay, and then so that I just tell you all this thing is quite interesting, important, so that if you understand this kind of thing, so that there's chance you can really get rich. And at least I tell you the real story about this kind of technology, so that I just tell you if you look at let me show you about this thing. At least I show you about that particular thing. You see about this additional information about microsensor and then OET. Okay, OET, and then it's become IPO. Okay, so that I did not tell you this is a real this kind of from basic research to all the way become the real product. So that of course it take a long time, take a long time. I tell you, it since 2005. My UC friend, okay, he come with new idea, right? Using DMD, this micrometer array, so that he can really create a very good idea about how I can create, you see, okay, DMD, you see, DMD, digital micrometer, right? And then try to optically, I can create some spatial force. So dielectrophoresis, some interesting idea, and then so that they can really manipulate this kind of a cell in much large scale. So this is something I told you, and then this is something in the video. It's briefly mentioned, but I just tell you this is something is a real technology, and so this technology turned into the real company, went to IPO, so that then you see here, went to IPO, and then so that let me see. Anyway, I just told you this is something quite amazing. So that of course, if interesting, you can look at this kind of keynote speech of CEO Berkeley Light, and so that to see, you can see went to IPO for 100 a big money, So that once IPO, then your technology, your company becomes super rich. I just tell you, this is Berkeley went to IPO. I just tell you, this is something. It's a real number. It's not something and then it's one of I think unicorn. I say $178 million IPO, and then so that and then if you're interested, this is one you interesting, you want to understand from this basic device we publish doing lab, right? Demonstrate good paper, and then become the real product. So that's something I tell you. I don't have time to show you all the detail, but at least this is something I just tell you that I witnessed about this kind
Good
of.
morning, afternoon, or evening, everyone.
I tell you, you have time, so that you may want to look at this real CEOs talk about how this kind of thing, how this kind of thing can be really become the real product, and then can reach. So that this is something I happen. My UCLA friend who did a PhD at UCLA, and then really make a important milestone. Of course, as I mentioned, UST do have one PhD student, Gary Lee. His company, Man Sensing, and then went to IPO as well, right? 2 years ago, and get rich. So it's something, of course, all these things, microfluidics can also be useful for this kind of COVID-19. So that, so this is, I tell you, this all this kind of biochip microfluidics now became to be quite important now, right? So that this is something I tell you, I just tell you a real important thing which is so critical now, right? So again, do you have any question? Any question? I just give you additional information, right? This video, I do believe, is something, although it's difficult for you to learn, right, about all the real the modeling, simulation, and fabrication thing is really take about 4 to 5 years to know all this kind of design of this kind of device, MEMS, microfluidic. But I tell you, this is something. Once you have this kind of good technology, then it's quite important and good reward for this kind of technology become real product. Okay, so any question? Of course, at this moment, let me just quickly show some of this kind of lecture note about saying pressure sensor is this in almost every smartphone. So do you know that your smartphone has pressure sensor, micro pressure sensor? Huh? Why your smartphone need a micro pressure sensor? Why? Any idea? Why pressure sensor, micro pressure sensor was used in our previous what kind of application we mentioned in our previous lecture? Huh? One student, Chi Yan, said touch screen. No. We mentioned in our previous, right? In previous lecture, what kind of how will you press sensor? Like 30 or 40 years ago. How? I hope you still remember. You say you attend the lecture, but if you don't study, then I don't think we mentioned touch screen for the pressure sensor application. The first thing we in our previous lecture, what do we mention? Huh? Well, we're going to have this kind of midterm exam. I do hope we describe this kind of several times, so that if you just no listen, don't study, careful to understand, then you may have problem. No, it's not blood pressure sensor. One of very, very mature application for pressure sensor is not for biomedical, it's not for smartphone. What's the application? Huh? Well, I do hope you understand. One of the most mature we mentioned in our previous slide. This lecture note. What I hope you. Any student still remember? In a car? No, it's not airbag. It's oh good. Finally, we have one student for engine. The one of more very, very mature this kind of pressure sensor in the I would say probably at least 30 years is for pressure sensor for the engine control. This is something we mentioned. Okay, we have one student Yu Tao finally provide a good this answer, so correct answers, right? So that the member we discussed this one, and I do hope you understand why. So that again, so this is something we just if you just don't carefully study, then so that then you forgot. Then say we do mention about this one in our previous lecture note. I was surprised most of you cannot answer this kind of very simple question. Huh? Let me quickly go here. We do mention this one. You see, pressure sensor, I do draw all this thing for this engine. I surprised that some of you cannot answer this kind of simple question. Because why engine needs 1%? Because engine, what engine? Engine basically is we have to use mix this kind of air with this kind of oil, right? Gasoline, and then by right mixing of this kind of air, oil, right? Air fuel mixing, so that optimize this kind of a ratio, so and get best kind of combustion process. So this is something. Let me just try to describe again, so that this kind of pressure sensor is used to control this kind of mixing of air and this kind of gasoline, the oil, fuel, especially oil. Why? In engine, car engine. so that you have much more efficient way to run this engine. So this is something, of course, later on we also mention why, so that we also have this kind of pressure sensor used in the tire monitoring, TPMS, right? So that something, this is one most mature tire pressure sensor is TPMS is another one later, right? Become much cheaper, so that the TPMS, I think we mentioned about TPMS, right? In here, TPMS pressure sensor for tire, increase the safety. Okay, so that this is something we already discussed now at least multiple times. I got 2 days ago. I do hope that you can really understand. Don't I do say, of course, pressure sensor also is it in your smartphone. But why we pressure sensor in smartphone? Why? Why we use pressure sensor in smartphone? Smartphone pressure sensor is using as sometimes they call barometric pressure sensor. Okay, what's this kind? Barometric pressure sensor in smartphone. Okay, so basically this is the sensor try to look at this kind of altitude or something. Now every smartphone will have GPS, right? GPS, okay, we have a good student, Jing Ho mentioned, yeah, it detects this kind of altitude high, so that then it's quite important. Why? So that so our every smartphone have this kind of GPS, right? Which can provide this kind of coordinate system, right? Provide this kind of X and Y coordinate system, right? Why for navigation? But if you try to go through some kind of a tall building, why, or and then in this case, the kind of pressure sensor, barometric pressure sensor can provide this kind of altitude. So that in this case, for navigation, so that navigation is quite useful. Okay, navigation is quite useful. Okay, so that of course, one student mentioned touch sensor. There are several ways to make touch sensor for a smartphone. One is capacitive touch sensor, another is pressure, like array or pressure sensor array. So there are several ways to make touch sensing for smartphone. Okay. Okay, so here I just mentioning about this. Now let me go back to the lecture. Typically, we have 2 types of pressure sensor. Basically, is first is we need have what? We need have this kind of diaphragm, very flexible micro diaphragm, and then so once it apply some pressure, and then it could cause deformation, and then so that in this case, I mean, so we have pressure apply, right? Pressure apply, and then cause deformation, mechanical deformation, right? And then in this case, deformation, I mean, we can call maybe X trend deformation or the displacement X. Right? And if we try to use maybe 2 types capacitance sensing, if we have a pair of microelectrode, and then a pair of microelectrode become what? Capacitor. So once you change delta X, and then we change the kind of capacitance. Why? So in this case, from input pressure to displacement, why? And then we have C. Why? So in this case, we can try from P to C, change of this kind of C capacitance. Then we can make this kind of capacitance. Of course, once you have a change capacitance, and then we can convert it to some, most likely is voltage signal. So all this kind of our CPU or processor, MCU, microcontroller unit can read this kind of, have ADC, read this kind of voltage, right? So that this is a voltage, this thing. And of course, There's another way is we have piezo-resistant sensing. That means if you can have silicon to some doping, either N-type doping, an impurity or P-type doping, and then in this case we can change the kind of resistors into the piezo-sensitive sensing. So in this case, we have sensing with P, apply the pressure, and then cause displacement delta X, and then change resistance, right? So that this one with P and change this kind of delta R resistance, then we can measure. This is a very basic way. As I show you, we are able to make this kind of pressure sensor, micro pressure sensor. Of course, why we need to make a micro pressure sensor? Because we make it much smaller, much cheaper. So this is also quite interesting. Why? So that of course in real product in your smartphone, it's not only my pressure sensor design. So of course this requires you understand sound mechanics. Okay, and then also this kind of thing, piezoelectricity, and then for the real pressure sensor, now it's not only the kind of very thin, this kind of diaphragm. This is on top view, right? Just I'll say here on previous slide we show you here, right? Once the pressure we call deformation here, right? So that then we have integrate this kind of electronics, analog, this kind of signal conditioning circuit, and even digital signal, because this kind of output from sensor, the signal too small. We need amplifier this signal so that most likely we have some amplifier, the very small signal from our sensor in micro sensor, so that we need to have a very good the kind of a design about this amplifier circuit on this kind of NIC design. And then also sometimes many of a computer, smartphone, we have digital electronics. So we have convert this kind of analog to digital. So that's why this has become quite important, right? So that again, so this kind of pressure sensor has existed for we can say almost 30 years. Maybe I would say it should probably change into 40 years now. Okay, so that and then start from first this kind of integration 1970, but now you see every smartphone have this kind of low cost man pressure sensor. So this is something I tell you it become quite important thing. Yeah. And of course, to make this thing to happen again, it's non-trivial. As I told you, analog IC design require about 4 to 5 years. You need study in the PG. Okay, so that this part is non-trivial. Okay, typically require about 4 to 5 years, minimum 4 to 5 years. You learn about this now to in a PG study, so that you are able to design this kind of NIC. As I mentioned before, right? So that why the ZTE in Shenzhen got US ban. Actually, US government banned this kind of high speed analog IC, so that once you ban ZTE in Shenzhen cannot buy the chip or this big company collapse. So this is one of very critical these things. So of course, NIC again is non-trivial, so that NIC design, the chip design is non-trivial. So that of course, as I mentioned, that Professor George Yuan, our colleague, actually has a company to work on NIC design, receive $100 million now for his start company. So that's something it's non-trivial, but it's critical. But if you know how to work on the design and really make a real product, so that this is something, especially at this moment, it's you can easily get this kind of funding from government, from this kind of VC. So that of course, as I told you, I have this kind of $30 million to hire postdoctor on main sensor, this kind of NIC design, so that now I'm very busy on hiring a lot of postdoctor. So that this is something is to tell you that this is both government and also this kind of VC they interesting invest this kind of very good this kind of microchip, right? Semiconductor chip and also microsensor chip. So this is something is very important. Okay, and another thing is oh, by the way, for this one, I do think all of you may want to look at those your smartphone app. I do think you can look at that particular apps to look at how now in smartphone, right? So that I do believe every of you have smartphone, so that you can easily look at this kind of barometric pressure sensor. So that this is something. Let me quickly show you this kind of thing, and so that at least I do think almost every smartphone have this kind of barometric pressure sensor. So it's something becomes so low cost and mature. If you look at your smartphone, and I do think both Android and iPhone iOS system have this kind of a barometric pressure sensor app. So that of course, last time I also mentioned that you can also download sensor kinetics, so you can look at all the sensor in your smartphone. Okay. And another important thing is about mains accelerometer. I think also mentioned in this video I just showed you, right? So that how this kind of micro accelerometer work. Basically it's a meter, right? It's a meter to measure acceleration. Of course, sometimes in those smartphone company, they don't call this micro accelerometer look what G sensor. If you look at the Apple, right, iPhone, they sometimes call the G sensor. Okay, so that if you download this kind of sensor kinetics, then you can really look at how you can get this kind of real data from your smartphone accelerometer. So that's something is important. Here I just briefly mention how this accelerometer work. Basically is very simple. Again, you have a micro mass spring system. You have this is very tiny mass, and you have spring. This is MK, micro mass spring systems. Just like we have interesting simplified here. You have micro mass and spring system. Okay, this is mass and micro, and then once you have it move around your smartphone and what happen, and then it causes vibration of this kind of micro system, micro mass spring system for vibration and functional time. So if you have good design, so that this vibration can what change called deformation of spring. This is micro spring. Okay, this is a okay. This is you can micro beam. I would say micro beam, micro spring. Okay, so once here and then again you have once you have an input acceleration. Okay, maybe G. That's what G sensor. Right, encode this displacement of spring. Displacement, right? This is originally maybe it's here, and once vibration, and then you can change maybe here, right? You code this here, and then vibration, a function of time, and then if you can convert this kind of a vibration into what electrical signal, and then for example you have a micro. There are two micro electron become change capacitance. So in this case, once you G into acceleration to X and to what? C capacitance. While we two pair of electron, and then once vibration, then we can input acceleration, output capacitance, and then you can do this kind of measurement about this kind of acceleration. So this is very basic thing, can show you how these kind of device works. So that without going too much more detail, but at least this very simple way. And of course, in real product, it's non-trivial. In order to have very good design to real product, you can look at this kind of thing. Basically, you have much more sophisticated folded spring. Oh, this require you have studied a lot more mechanics, sound mechanical design, so that this require a much folded spring, and also not only simple one pair electrode, you have a series of micro for capacity sensing to improve performance of this kind of real product. Do you understand? So that this is something I tell you in reality, right? So that previous slide show you very basic concept, but in reality, you need a lot more engineering design, I think, to become good design. And then of course, the sensing to the this kind of pressure sensor, we also need to integrate this kind of analog circuit, right? Amplify very weak signal. For example, design some kind of operation amplifier circuit, right? And then turn into the digital signal, right? So that so this is they do have a series of this kind of design in terms of micro machine design and also NIC design. So it's as I told you, it's still non-trivial, but now it's become so common now. Every smartphone or even smartwatch has this kind of motion sensor. Right? In the video I show you, right? They also use the kind of maybe VR, AR, MR. So all this need this kind of man's motion sensor. It becomes so important. See, yeah. So you can see now I would say every year. Do you know how many this kind of pressure sensor was fabricate? That's quite important for you to think about how big is the market. How many this kind of man's motion sensor was fabricated every year? Do you have an idea? Huh? At least billions of this kind of low-cost man sensor was fabricated every year for billion. It's billion. One student chuck one is not 100 million. Billions of this kind of a man motion sensor made, okay, every year. So it's every year. It's a quite important business, I say. It's not chuck one. I told you this area keep expanding, so that for those of you want to get rich, this is areas quite of course. If you don't know how to make a pressure sensor, but if you have know how to use kind of a sensor for real application, right? Like our friend Wang use man's motion sensor for man's motion sensor for jaw, of course, especially man's IMU for jaw, and then so that also quite important. Consumer jaw, right? Just like our DJI, so that this is something. Then so this is something. So anything now, I would say the micro sensor becomes so important not only for smartphone, smartwatch, smart building, or the smart self-driving car. It's one of a quite important technology. Now, so that of course this kind of sensor is going to expand a lot more. Right? Of course, as I show you, this is a very sophisticated design, micro mass spring system, right? And now all the iPhone, smartphone has this 3-axis motion sensor, man's accelerometer, and also gyroscope. Gyroscope also quite important. Basically, how the gyroscope work. Traditional gyroscope is very large. It's like spinning this kind of mass system, like in the probably World War II. So that the kind of traditional mechanical gyroscope is quite important for navigation and control for airplanes, but that is being miniaturized. Right? Traditional is a gyroscope, most likely is spinning mass. Okay, mass. This kind of mass spring system. Right? For traditional mechanical gyroscope. Okay, but for our smartphones, gyroscope basically is a micro mass spring system. Is basically is also mechanical mass spring system. Okay, but it's still micro mass. You have this kind of inertia M and K micro mass spring system. So that once you have a harmonic vibration, and then you have linear. Once you rotate your smartphone, and then you can this kind of correlates force, right, and induce additional deformation of microspring, so that once you have this kind of omega angle, rotate your smartphone omega, and then cause this kind of deformation of this kind of X, and then you define into C, right? So omega is angular rotation of smartphone, and then you change it become electric signal. So this is a very basic thing now, how this kind of micro gyro work in your smartphone, okay? And of course, I tell you this kind of real picture about iPhone use ST microelectronics, see, and then also of course you also have a micromagnetic sensor, as digital complex. This company in Japan, Asahi Kasei, is one of #1 company make a low cost magnetic sensor for every smartphone. It's something basically it's Hall effect sensor, okay? So that measure this magnetic field of the Earth, right? So you have this kind of digital compass, okay? You also have additional app, right, in your smartphone. And of course, DMD will show you, you can see 20 years, almost $1 billion R&D finally become real product. Only one company. That's why several company in mainland China, they are really try to think about how to make their own thing. One student also asked, well, green building including midterm, of course. You sent to green building we have discussed at least about more than 1 or 2 weeks ago. Definitely green building we're including in this kind of exam for sure. Yeah, there's no, yeah. And then, okay, so that of course, main motion also of the kind of main motion for what? Segway. So this is something quite important for motion. And then I think we almost run out of time. So in our today's video, we will show this how especially it's electrostatic. It kind of once apply voltage, electrostatic force, it can turn this kind of a micromirror, right, in one digital way, so that this is quite useful for computer projector. There's a series of companies in mainland China. They buy DLP or DMD for real product. At least one company in Chengdu, they went to public in, I think, in mainland China stock market. But you see, that's something, if the US government ban this TI to sell this thing, then this company collapse. That's why I have a project, ongoing project, how we can make micromirror. See, in case the US ban this kind of US chip, then so that I do think it's quite important to make our own. Of course, DLP chip can also use to make TV and also VR, AR. So this is quite important. And see, I think we run out of time. So again, do you have any question for today's lectures? Today's lecture, for those one we have discussed, we will not cover today's lecture, but there's an overlap, right, by basic concept of a micro sensor. So it's covered, we discussed in previous lecture will be covered, okay? Okay, so that, anyway, so that will not give you those kind of new content today, but all I would, at least all of you have learned about this DMD, right, last time. So we cover in our midterm exam. Okay, any additional question, please feel free to ask question on our Canvas discussion thing, so that please, I think we have not too many students ask question. I do encourage you ask question. Okay, bye-bye. Okay, bye-bye.